Another time-dependent problem that we're going to discuss today and continue next time is the NMR problem and nuclear magnetic resonance. So this is a pretty interesting problem, nuclear magnetic resonance, and it all begins by having a magnetic field that has a big component here, B naught, I think. It's a good name for it. B naught Z, indeed. And then you're going to have some magnetic field that is going to be rotating here in time in the xy plane. We'll assume at time equals 0, it's here, and then it's rotating with some angular frequency omega. So the total magnetic field is B naught Z hat plus some number B1, and I'll write it here, plus B1 cosine omega t times x hat minus sine omega t times y hat. So indeed, in the xy plane seen like this, you have it here, and it's rotating with angular frequency omega this way, clockwise. All right, so we have this magnetic field, and of course, we're going to try to figure out what spins do in it. And the magnetic field is time-dependent, so we're in risk of getting a time-dependent Hamiltonian. So what is the Hamiltonian? This possibly time-dependent is supposed to be minus gamma B times the spin. So what is that? It's minus gamma B naught SZ, because the x component matches with the, the z component matches with the z component of the spin, plus B1 Sx cosine omega t minus Sy sine omega t. And, well, it's as bad as you could imagine, pretty much. This Hamiltonian is time-dependent, and there was some good news. Even if it's time-dependent, they commute at different times. The time evolution is easy. But no, they don't commute at different times. At time equal 0, for example, you have Sz and Sx. But at a later time, you would have Sz and Sy, and they just don't commute. So we have no cookbook recipe to solve this problem. We have to figure it out. There's several ways to figure it out. I had a way to figure it out that I explained previous years, but today I suddenly thought I could explain it in a different way. That is maybe a little harder conceptually, but explains more of what's going on. So this is what I want to try to do now. And basically, what we're going to try to do is get the main intuition going for this problem. I have a Schrödinger equation for this problem that is very complicated with a time-dependent Hamiltonian. So, if you have a wave function, and now I'm going to be a little rough for a little while, IH bar dt h psi. And it evolves, oops, what is it? Let's see, which lights? Lights, general. Okay. So if you have a problem like this, you might say, well, I would like to do something non-trivial to this. So I want to maybe change the Hamiltonian and do the same physical problem. Now, that's not easy, because if it's the same physical problem, how can you change the Hamiltonian all that much? So one thing you could do is you could try to change the states by doing a unitary transformation, and then hope that the unitary transformation acts on this Hamiltonian. So this will be the new states. And you would hope that this unitary transformation would somehow, working with these new states, would simplify the Hamiltonian. But unitary transformations in general is just like a change of basis that is not going to do all that much, unless the unitary transformation has time dependence, in which case it doesn't just rotate the Hamiltonian, but messes up this term. But this is really your only possibility of fixing things, is to try to do a time-dependent unitary transformation that somehow you started with a spin Hamiltonian, and you're going to do a unitary transformation, and perhaps is going to be a time-independent one. But this u is going to depend on time. And this is not the whole Hamiltonian, because there's a problem with this part. So the idea is sort of vague, but you're getting a little of the gist of what we try to do. So the first thing I'll try to do is something maybe intuitive about this system. I could say that suppose I have a system here, and the Hamiltonian is 0, nothing. Nothing happens in that system. Now, the thing that is curious about this, that this magnetic field is rotating. So let's try to imagine how would physics look if you have the xy axis and you have the xy axis rotating with angular velocity omega. So the xy in the plane is rotating with angular velocity omega. What would happen? So there's an hs that is originally 0, that you say it's 0, and then any spin state stays there. There's no time evolution, h is equal to 0. Nevertheless, if you jump into this rotating frame, all the spin states that were static, for you, they're rotating. And in fact, for you, they are precessing around the z-axis if you're in the rotating frame. Therefore, in the rotating frame, you must have some Hamiltonian, even though there's no Hamiltonian in the static frame. Because in the rotating frame, you see things spinning. So in the rotating frame, if there's a static spin along the x direction, you now see it spinning around the z-axis with frequency omega, in fact, going in the plus z direction. So in the rotating frame, you can ask, what is the new Hamiltonian in the rotating frame? And in the rotating frame, the Hamiltonian should be such that it rotates the spins with angular velocity omega around the z-axis. You may recall that this is done by the unitary operator e to the minus I omega t s z hat over h bar. This is the operator that rotates spins with omega t around the z direction, which is precisely what you want this Hamiltonian to do. So the Hamiltonian must be e to the minus I h t. So this rotating Hamiltonian must be omega s z hat. So the Hamiltonian in the new frame is that because that Hamiltonian produces the rotation of states that you see, because your friend that is not rotating is telling you that no state is moving, h is 0. So the intuition is that you've passed from the original Hamiltonian to this one, and you had to add this. But what we'll see now is that you have to add a little, you have to do other things a little if this is not equal to 0. So here is what we want to do. Now there's also a couple of ways of doing this, but let me try a little calculational way to do this second part. So we're going to take, therefore, to have, for example, a psi r, a rotating wave function that is going to be given by a unitary operator times the physical wave function you want to solve. This is what you want. And this is what you hope has a simpler dynamics, psi r. So let's try to figure out what is the Schrödinger equation for psi r if you know the Schrödinger equation for psi. So I dt, IH bar dt psi is equal to Hs psi. Let's see what is the Schrödinger equation satisfied by this one. So IH bar dt of psi r is IH bar dt of u psi. So let's differentiate this. This is IH bar dt of u, and I will have the psi, but I will put then a u dagger and another u acting on psi so that it gives me psi r. So the first derivative is acting just on the u. I acted, and then I put u dagger u and recreated the psi r. The other term is in which it acts on psi. So I get plus IH bar. The u goes away, and now I get dt of psi, which is IH bar dt of psi is Hs on psi, so I must delete this. So the second term, when I acted here, I act with the whole thing. IH bar ddt on psi. The u is out, and I put Hs psi. And here I can, of course, put a u dagger u and put back the psi r, so I will do that as well. U dagger psi r. So actually, you have now a new Schrödinger equation, which is of the form IH bar dt of psi r is equal to u Hs u dagger plus IH bar dt of u dagger times psi r. Now, that's it. This is the new Hamiltonian. This is the rotating Hamiltonian, essentially, that we're trying to figure out. That is going to be simpler, we hope. And there we go here. We have this similarity transformation of the Hamiltonian, and we have this extra term. Now, this suppose the original Hamiltonian had been 0. We want the new Hamiltonian, given our argument, to be this for the rotating system. So I will say that this u is such that you get IH bar dt u dagger being precisely omega sz. And for that, the u is nothing else but e to the minus I omega t sz over h bar, which is in fact that thing that we had there. So that's what u is, and in that way, this whole term becomes just omega sz hat. So we're almost, in a sense, done with this thing, because we have made some good progress, except that we still don't know if everything has worked out or not. I'll continue here. And just 1 minute to close up the discussion by saying what has happened. So what has happened is that we have found that there's a new Hamiltonian, HR equal UHS U plus IH bar DTU U dagger. And then U is given by e to the minus I omega t sz hat over h bar. And psi, as we said, psi of t is equal to e to the I omega t sz hat over h bar psi r of t. So this came because we said that psi r was going to be u psi, and therefore I took u and the inverse, and you get this. So look what the problem has turned into. It has turned into a problem for psi r with a Schrödinger equation that has a Hamiltonian HR, in which this piece is very simple, is omega sz hat. And now the crucial point is whether, here I have u dagger, whether this thing is time independent. And this should be time independent if we got our physics right, and that's exactly where we will take on next time, and prove that it's time independent, and then we can solve the complete problem.